So now that we have been introduced to the fact that not all acids and bases are created the same, we have to go over how to do calculations for that. Again, probably don't have to jot this down because this is just what we went over. But recall that a weak acid does not completely dissociate. So in other words, when you took the molarity in our warm-up problem and just said that that was the hydronium or the acid concentration, and then from there you could solve for the pH, life was easy. But if this does not completely dissociate, then this molarity is not the hydronium concentration. And if that's the case, we need to do more math in order to figure that out. And that's what we're going to work on today, is what more do we have to do. Okay, so one of the equations on your equation sheet is just your normal equilibrium, but it's for Ka, equilibrium for an acid. The nice thing about this is equilibrium constants are known for weak acids and weak bases. And if you know about your equilibrium values, the larger the value is, the stronger the acid is. The smaller the value is, the weaker the acid is. So we can look at those. I mean, there's that problem where it gave you HSO4 minus and HCO3 minus. And I looked at it and I told you guys, hey, the HSO4 minus is the one that's going to act like an acid. Well, there's an equilibrium constant that can probably back me up with that statement. I'm going to go back to this reaction that I showed you that we ended our last notes with. And remember, to solve for K, it's the concentration of the products divided by the concentration of the reactants. However, water is not an aqueous thing. Water is a pure thing. It does not have a concentration, which is why in this particular problem, which will be similar to other ones that you do, to solve for the equilibrium constant of an acid, you're going to take the acid ion concentration, which is either written as H3O plus or just H plus, times the conjugate base. In this case, it's the fluoride ion, divided by the acid HF that started this all off. So again, up on the smartboard you have for this particular problem, up on the whiteboard is the generic way of showing it, which is what's on your equation sheet. Okay? So, here's what we're going to do. We're going to go over a problem where, what if I start off with 0.25 molar hydrofluoric acid, and I want to know what is the pH for this? I'm going to set up an ice table. After all, if it gives me a double arrow, I know it's an equilibrium reaction, and that's where the ice table is a good way to organize what I need to do. So I have the initial concentration of HF, which means I start off with nothing of both of the products. I recognize that one thing's going to change by an amount, let's call it X. Other things are going to gain that X value, and then I have my equilibrium. In order to do this, I would have to know the K value of that particular acid. Well, hydrofluoric acid has a K value of 7.1 times 10 to the negative fourth. What I'm going to do is switch over to Smart Notebook then to write out how to solve this particular problem. But there's a reason why we did equilibrium prior to this. This is the same type of calculation. So, the K value, again, was given to me as 7.1 times 10 to the negative fourth. That would equal the concentration of the products. Well, if you look back at your ICE table, that was X and X. So X times X is just going to be X squared. Divided by the concentration of the reactant was at 0.25 minus X. And hopefully this looks familiar to us. And you have two options at this point. You can multiply both sides by 0.25 minus X to get rid of that in the denominator, and then get everything to one side, and now you are using the quadratic formula, which you don't want to do. Or you can recall from the previous unit that since this K value is fairly small, and when I say fairly small, it's about 1,000 times smaller than the molarity that you start off with. That's a good indicator. Since that K value is small, what you can realize is the minus X is a tiny, insignificant value. Now, you can't just get rid of multiplying by small numbers, because multiplying and dividing by small numbers will drastically change their values. However, we can get rid of either adding or subtracting tiny, tiny values. Which now means we have 7.1 times 10 to the negative fourth equals X squared divided by 0.25. Well, multiply both sides by 0.25. And that give me 1.775. I'll just keep the extra digits right now. Times 10 to the negative fourth equals X squared. Take the square root of that. Now I will go back to my two digits here, 0.013. This X value is, if you look back up in your notes, the same as the hydronium ion concentration, the same as the fluoride ion concentration. Take 0.25 minus this would be how much hydrofluoric acid is present. What we wanted to solve for was the pH. That's the main thing that you're going to be asked to solve for. Some students, it's kind of confusing of, hey, wait a minute, if I have HF, isn't that the acid? Well, yes and no. We identify it as the acid. However, what gives it its acidic properties is that H plus ion concentration. It's this part right here that's what makes the pH what it is. Now, perhaps this would be easier when it comes to sig digs if we rewrote it in scientific notation. Because remember, our rules for significant digits, what I started off today with was that if you take the negative log of that, and I'll give you a whole bunch of digits that the calculator says, 1.875400821. If you take the negative log of that, there is a number that represents what's in front of the decimal. Then this has two digits here for two digits there. Since that's a 5 after, I'd round this up to 1.88. Now let's say we started with a base instead. So remember, we can do this for weak acids, we can do this for weak bases. You're doing the same general setup, a set up an ice table. You'll probably end up doing some sort of x squared over initial concentration minus x equals the Kb value. But when you solve for x, you'd be solving for the hydroxide concentration. So if you took the negative log of that, that would give you the pOH. You'd have to do one more step then to solve for the pH. So bases have that one additional step that you need to do as well to make this work.